Hello everyone. So today I'm going to show you how to start with ANSYS Fluent, like very fundamental stuff. Start with the most basic simulation, like how to select the option, like why are you selecting those options, going through the Fluent tutorial. So to start, just in the search toolbar, or if you have a desktop icon, just type Workbench. If ANSYS is installed in your computer, uh, you can open the Workbench first, not directly Fluent, but Workbench. Workbench is a managerial tool. This is not the solver, but it manages all the solver ANSYS has. It's easier to go do a safety type of simulation using Fluent solver using the managerial tool. So I'm going to show you the most convenient way of doing it. So I opened up the ANSYS Workbench. As you can see, these are all the analysis system. Analysis system means you can do a complete fluid flow simulation using this Fluent package. Like if you hold the left click, left mouse button and drag and drop it, you'll see not only Fluent, but the whole system, like the geometry, the mesh, the setup and the solution and the results and everything. So it gives you that complete package when you are trying to do a CFD simulation using Fluent Solver. So in the setup, the Fluent interface will be opened. But if you want to individually just like you already have a mesh file somewhere and you just don't want to do the geometry and mesh in here, so you directly want to go to the setup, what you can do is you can go to the component system. So basically this analysis system has 1, 2, 3, 4, 5 component systems. Similarly, you can just drag and drop, and as you can see, we only have the Fluent setup and the solution. So this is a component system of the whole analysis system. Similarly, if you just want to display the results, as you can see, just the results. So you can drag and drop. You can delete it this way. You can drag and drop component systems or a complete analysis system. All right. So I'm gonna do a very simple problem today. Flow through a rectangular channel. Okay. So remember two things. This is what I'm saying is this is a rectangular channel, and the green box is like green marks. This is nothing but a cross-sectional area I wanted to display in this rectangular channel. So imagine flow is going through the left frontal point and going out to the back. Okay, let's say uniform flow coming in. So if you want to analyze this kind of scenario, like imagine you want to simulate a river channel or maybe a rectangular duct, okay, something like that, long like rectangular duct. So what we usually do, you can do a 3D simulation, but that's computationally expensive. So what you want to do is you want to make your uh, model simple. Depending on your problem, you want to make your model simple, but simple like there is a limitation. If you're trying to simplify everything, you'll lose accuracy. Like in this kind of problem, we can take a rectangular cross section in the middle, do a 2D analysis that would give us a good numerical results. Why? Because if you see the near the wall, there will be shear stress, or if you say resistance to the flow will build up opposite to the flow direction. But in the rectangular channel, the side walls are far away from the middle one, right? So if we take a cross section at the middle and do a 2D analysis, the resistance from the side walls to the middle section will be really negligible. But imagine if you have a uh, circular pipe like that. Okay, so if you take a cross section in the middle like this, if you take a cross section in the middle like this, It should have quite a good influence from the side wall as well, because this is curved. Near this near the top part, there will be resistance to the flow, shear stress acting on this cross-sectional area, and the flow will change. You'll see maybe close to similar behavior in some certain condition, but know this, this would become it should be completely different. It should show a correct behavior, but if you want to analyze the pressure, the temperature, the properties, they will deviate up to some certain point. So I'll tell you how to do this kind of problem using this simulation, but let's start with the most simple one, the rectangular one. So we have this rectangular channel or pipe, and so we want to do an analysis of the flow through this rectangular duct, let's say. So we took a cross-sectional area in the middle, and this is our problem description. So this is that cross-sectional area. So flow coming in from the left with 1 meter per second velocity, inlet velocity, uniform velocity in all over the area. uh, the height is 0.2 meter. The whole system is at atmospheric pressure, which is 101.3 kilopascal. The length of the duct, like the length of the flow, is 3 meter. And flow going out, we don't know the outlet velocity, and we don't know the velocity distribution inside this cross-sectional area or the pressure inside this, like maybe the pressure drop across this pipe. Yeah. So this is the fluid properties. I said, so this is not practical density and viscosity. So I made some simple, I gave some simple values so that you can understand it better. If you're using water, let's say as fluid, the rho would be 1000 kilogram per meter cube. Dynamic viscosity would be something, I think, some values, and then we calculate the Reynolds number. So imagine we have this problem, we have a uniform velocity coming in, what would be the outlet velocity? Okay, so this is the problem we want to analyze. Okay, we want to check the velocity distribution, velocity control plot along this flow, the pressure distribution, and also check the outlet velocity as well. Okay. So let's start. If you want to do the geometry, you can right click on the geometry. So there is right now there is in this version there is two design tools. You can also import your geometry if you have a complicated geometry, complicated 3D geometry. You can do it in SolidWorks or other softwares, NX or AutoCAD. So you can import those geometries over here and then work on it. But if your geometry is simple, like the one we are going to work on, you can use one of these design tools. I'm familiar with the design modular, so I'll go with the design modular. Let's wait a bit. It's opening up. So we're going to do the geometry and then divide the geometry into small elements. So that's called meshing. Okay, it's opened up. So we're going to do a 2D geometry, right? So I'm going to just use XY plane, and I want to create a sketch in XY plane. So here it says new sketch. Okay, so new sketch. In this sketch, okay, in this sketch, you can right click and look at to directly move to the, like you're directly looking at the sketch one right now. You can use these tools to go back to isometric geometry, Z, X. So up to you. These are good tools. So I'm gonna go back. So I want to create a rectangle, but before that, go to the top and select units. I don't know if you can see that. Maybe my video is a little bit smaller. So on the top, there is a unit, so make sure your unit is right. So we are going to work on the meter, so I'm just going to select meter, but you can change the unity here, and it should be displayed in here somewhere here. Okay. So I selected the sketch. I'm in the modeling right now. I'm going to go to the sketching. So there is these drawing tools. You can go down. There are other tools as well, like circle, ovals. I'm going to work with the rectangle. Okay, rectangle. And one thing you need to know is that, as you can see, if I go close to the axis, it says C. C means coincident to the axis. Okay, but if you go to the centermost point, you'll see the C becomes P. P means the point. So P is the point 0, 0, 0. Okay, or maybe some interaction point, intersection point in your geometry you want to select. Make sure always the P is there. Otherwise, if you just randomly select and the P is not there, there will be a very small gap and the geometry might not work. So make sure the P is there. Okay, so left click, start, and then maybe I'll make it small initially. Okay, this one. You can scroll it to zoom, or even use this one to zoom to fit. Okay, uh, and then go to the dimension, general dimension. I'll just use a general dimension. Like you can use vertical distance between two lines or horizontal distance between two lines using this tool. So anyways, just play around it. So I have my horizontal one. You see, it says H1, and this one is V2. So here in the dimensions, as you can see by default, I just dragged it, so it's 4.46. But now I know from my geometry, my length should be 3 meter and the height should be 0.2 meter. So let's fix this. 3 meter horizontal distance and 0.2 meter vertical distance. So this is how our geometry looks like. So we just created the outline of the geometry. We need to create a surface in which the fluid can flow. Okay, so and make sure before creating a surface, this outline is closed, like there is no gap between these two lines, there is no open points. It's always a closed point, like these two lines are connected by a point, these two lines are connected by a point. If it's discontinuous, the surface will not be created and you will see an error. Okay, so how to do the sketch? So after we have finished doing the outline, so the sketch, you can go to the create at the top, and so I'm going to the concept. You're right beside the create, the concept, and surface from sketches. Okay, because I want to create a surface and I have just a single sketch in here. So base object is a sketch, so you can either left click on any of these lines. Okay, it will select the sketch automatically, or you can select the sketch in here as well. Okay, apply. You see the sketch is selected, not the line, but the whole sketch is selected. And generate. So this is my surface. So if you go over here, selection filter, so now I know these are my edges. Okay, so this is the outline I created using this sketch, and my surface is created. So this selects face. So as you can see, the surface is created properly. There is no error in here. And also a part and a body is created, a surface body is created. Okay, and this surface body by default it's defined as solid, so you can define it as fluid. You can do it later as well, but it's easier to do it in here. Okay, so I'm not considering anything about thickness of this rectangular duct. So we just want to analyze the flow because we are not considering the temperature from outside or anything like that in this problem. We just want to analyze the flow, how the fluid is flowing, the flow distribution, the velocity distribution, and the pressure distribution due to the fluid flow. Okay, so that's why we're only considering the fluid body part. So we have this fluid body, internal fluid body, and I think we are done with the geometry. Okay, you can, if you want, you can rename this one. Let's say uh, fluid domain, fluid domain. Okay, just so that you know, like which one is it. Like sometimes you have multiple surfaces, so renaming is important. All right. So after you have finished doing it, before closing it, go to the workbench, and as you can see, a green tick mark is over there. So geometry is completed properly. Now, if you want, you can just close this one, or you can leave it open as well. Doesn't matter. So after the geometry, the next component system is meshing. So what we are going to do in the mesh is divide this surface into uh, small elements, small segments. This is called discretizing. So we are going to discretize the geometry. Okay. All right. There you go. It can. So this is our geometry. This is our surface. But as you can see, there is no meshing, and the mesh. You see this yellow bolt mark right beside. So mesh is not generated yet. So you need to click over here, generate mesh. Just click over here. And as you can see, it became green, right? So I just selected the most default features, like default sizing, quality, inflation. Like I just went with the default features, and this is the mesh that is generated by default. Like here, excuse me, this is 1 2 3 4 5 6 7 8, some maybe 15 elements. If you want to check like how many elements, you can go to the statistics. As you can see, element is 20, so there's like 20 boxes like this over here. Okay, so I divided this surface into 20 uh, elements or cells, you can say. But is this good enough? Like how much? Like I will like the equations, the Navier-Stokes equation we're going to solve is for each element because this is a finite volume approach. So we're going to solve for this volume, the second cell volume, the third cell volume, and so on and so forth. But there is such a big element in here. Like how will I calculate the resistance from the wall, which is called the no slip condition in here. So like what would be the no slip condition from the bottom and the top on the fluid flow? Because there is no division in here, so it's very difficult to calculate, and that's most probably because this is an approximate method, it most probably will be inaccurate. So what we can do is, because we will lose the resistance calculation from the wall to the middle, there will be like a, velocity, low velocity near the wall, high velocity near the middle. But if it's one cell, we're not going to be able to see that one. So what we need to do is increase the number of elements near the wall. So depending on the problem, you'll do the mesh. Okay, you want to do a very efficient mesh. Uh, you need to know, like in your problem, where is the critical region, and in that critical region, you want to have as many elements as possible. Like in this problem, we know near the wall, due to no slip condition, we will have um, velocity change by a lot. Okay, so but in the middle there will not be that much of a change. So we need to increase, like have a higher number of elements near the wall, and lower number elements we can have near the middle part. Okay, so how do we do that? The easiest way to do is using the mesh controls. Like initially I would do this one. Let's see, the most standard way to do it is um, I think anyways, let's show you the mesh controls first. In the mesh control, you can use the sizing over here. So this is uh, overlapping on the default features. So this will be prioritized over the default features. Like the features you have over here, it has sizing as well, but your manual sizing option will overlap like overlap the default sizing features. Um, so geometry, this is the surface. Make sure the selection from here, the face is selected, and this one face we want to do the sizing. You can do a face sizing. You can even do a edge sizing. So from the selection toolbar, I selected an edge. So the top and the bottom, let's say I want to, I just press control and select both, or you can just drag along like this. Let me, okay, so you can just drag along like this as well. So these two edges are selected, or you can just click over here, press control, hold control and click over here. So those two edges are selected, and instead of the face, what I want to do is size these edges, because that's a better way to do it, as you'll see. So I have these two edges, the number of divisions. So it depends, like it's now based on the element size, but I want to make this one based on the number of divisions, because that gives me more control over it. Okay, so let's say I want to make the division 40, let's say. Okay, so as you can see, there is like 40 divisions in here, and you can just increase it by maybe 60 if you want. Okay, and then I selected two edges, number 60. Behavior soft means like if two of these mesh control methods is like contradicting, whichever is soft will be in the low priority list. Whichever is hard, if you say hard, it has to do it. Okay, it has to divide these edges into 60 divisions. If it cannot, it will give you an error. But the soft will just will not give you an error, but just go with the default features if it's not able to do it. Okay. Similarly, you can again go to the mesh control methods and do it, or the easier way to do it is right click and duplicate. By the way, you can rename this one as well. Rename it maybe horizontal, horizontal, this one vertical. So how about this vertical? So I duplicated the vertical one, right? So still it's the same thing doing. So what I want to do is uh, click over here and select your new two uh, uh, edges. Okay, click apply. As you can see, I just changed the edges. Still there is 60 division, but I don't need 60 division. It's too much, I think. You can right click and make the box to zoom in. So this is too much, so maybe I'll reduce it to 20. And let's take a look. I'll do the generate mesh thing over here. I'll generate the mesh. And if you want to see how the mesh looks like, left click on the mesh As you can see, it looks like this. Yes, it did divide on the top and the left part, but the middle is weird. Like it's highly concentrated in here, but middle they just ignored the command. So what we can do is make sure vertical is hard as well. Okay, and they just made an unstructured mesh in here. As you can see, unstructured means triangular mesh in here. Okay, not everything is rectangular mesh. uh, so what we can do is get another mesh control, face meshing. So what face meshing does is it selects a face and make the elements on that face structured. Like method is quadrilateral, so all the elements will be quadrilateral. Okay, generate again. Let's take a look. It should look better. You see? Oh, okay, there you go. So that looks better, right? But still, like the elements you see, it's not similar to square, but a lot like a big rectangle. But the purpose of having the elements near the like higher elements near the wall is satisfied, but have a long rectangular element. How do I avoid that? So what you can do easily is just increase the number of elements in here. Instead of 60, maybe 180. Let's take a look at 180 and generate again. Meshing is very, very important. If your mesh is wrong, it's always going to crash most of the time. So you see, now it looks a lot better. Okay, always try to make, if you are doing a structured mesh, always trying to make as square, make the elements as square as possible. Okay, as close to square as possible. Looks good, but as you can see, I have a uniform mesh all over the surface, which is not a very efficient one, because I don't need maybe this much refinement in the middle, but I need more refinement near the wall, because the velocity is going to, I know from the problem, the velocity is going to change a lot near the wall, and I need more close, like smaller elements near the wall. So how do I do that? Instead of, I can always increase the horizontal and vertical number of elements, but that's going to increase my total number of elements by a lot. So how do I make finer elements near the wall and larger element near the middle? So what you can do is go back to this vertical distribution, and what you can do is you can apply a bias. Okay, before applying a bias, make sure, check your direction of the edge. So select this one, it should display, and as you can see, the direction of this line is from top to bottom. Let's take a look at the other one. This is from bottom to top. So for the bias, the direction is important, and as you can see, the left and right side direction is in the opposite direction. So what will happen if we just apply some bias for both? Okay, so now, right now it's no bias. So this is the direction, like the beginning of the line would be larger, and then gradually it will become smaller. Or this is beginning is smaller, gradually it will be larger. There is also one, like both sides would be larger, both sides would be smaller, the middle would be larger. So we can just select this one, and this will, even the direction are different, it will not have any influence. So what you can do is select a bias factor. It just factors out like how much, like by factoring it, like how much growth rate do you want. So let's start with just, let's just play around. Let's just start with 20 and take a look. Let's just generate the mesh and take a look at it. So as you can see, I have smaller elements near the wall, larger elements near the middle, and because I selected both, uh, this became a good bias. But make sure when you're selecting bias, your direction of the flow is, just check it. In here it didn't have any influence because I selected a bias type where direction doesn't matter because it's symmetric, right? But if it's not like starting from a smaller point and the end point is larger, then you need to have maybe, like if I wanted to do it using a unidirectional bias, I had to do two bias. So I had to what I had to do was duplicate this one, and in this vertical part just the left edge, in this vertical two just the right edge, and then apply a reverse bias in here. Okay, there would be a reverse bias option. Like, let me show you guys. So let's say this is unidirectional. As you can see, this is the reverse bias option coming in. So whichever bias was in here, there will be a reverse bias in here. But anyways, in this problem we don't need to do that. Maybe in the future problems, if we have something like that, I will show you guys. So we're done with the mesh. Again, you can always play around. But start with a standard mesh, which looks good. Just start your simulation with one mesh, and then you need to verify, because we don't know if this mesh is good enough for our problem. We cannot say that. Okay, there are some consideration from some of the literatures, uh, but again, for this, like, you just want to learn how to use ANSYS, and you're not going through the literatures to learn the software. So what I would recommend is just start with any kind of basic mesh, and if you want to know, like, if this mesh is good enough, what you can do is run one simulation using this mesh, come back, increase the total number of elements by a lot, and then do the simulation again and compare the results. If it's not changing, then this mesh is good enough. So this is why, always remember, the beginning mesh should be very coarse. Coarse means like there'll be less number of elements. There'll be like a really large elements in here. Okay, so always start with a very coarse mesh and then refine it with time and check if the results is not changing, then this coarse mesh is good enough. Why do we start with the coarse mesh? Because we want to have as less number of elements as possible, because each element is gonna stack up to your computational time, and it's gonna take a lot of time. Okay, this small kind of simulation, it doesn't matter, but the large simulations, it is a huge fact for the simulation time to reduce. Like, it can save 2-3 days just by developing a good mesh. All right, after this one, the last thing to do in meshing is use the selected option. I'm gonna select edge and left click. So this edge is my inlet from the problem, right? So I'm gonna right click, create name selection, and this is an inlet. Fluent is name sensitive, ANSYS is name sensitive. So what it does, like whenever you name something inlet, it's gonna take an inlet boundary type. Okay, right click, outlet. Not like you cannot change it, but remember, like whatever name you like if you name this one interface, it will take it by default as an interface type of boundary. Uh, uh, Look, I didn't specify the top and bottom or the middle section. You can do that, but if you don't do it by default, like whichever is not defined, ANSYS takes is the edges as wall and the middle part as an internal region. So this is the same thing I was going to define, so I just skip this one. By default, it is the same thing. So I need to apply boundary condition at the inlet and the outlet. That's why I did inlet and outlet. Okay, so we are done. Make sure the mesh is generated properly, and I think I'll go to the workbench. As you can see, there is a yellow bolt mark over here, so it's not finished yet. Why? Because we didn't update it. So you need to update the mesh from here. Give it some time. So mesh is successfully updated, and as you can see, there is a green tick mark over here. You can also right click and update from here as well. Okay, but make sure it's updated. So we are done with the mesh setup. Just double click over here. So if you want to have a more precision, you can do double precision. Serial means how many processors you want to use. Parallel, you can use GPUs. I'm just going to use serial processor in here. So now the solver Fluent is opening up. All right. So as you can see, it uploaded its default mesh and everything. So this is the mesh. Now I need to select these options based on my problem. Let's go through one by one. So this is the general. You can check your mesh and always make sure to check if there is any, if there is this minimum volume, the maximum volume is negative or not. Because if it's negative, your mesh is not right. Okay, your simulation is not going to work. So check this one. You can check the quality. Just go through these things. You can check the quality in the mesh as well. uh, Display how do you want to display it? Like right now it's displaying everything. You can just ignore displaying the middle part and just display the outline even in here. Okay, you can specify these things. Now the main part is like how do you specify the solver. So this is a pressure based. I want to use a pressure based solver. Density based is mostly for the compressible flow where volume is going to change. Okay, volume of fluid is going to change, but we want to do an incompressible fluid flow. The fluid is not going to compress. Velocity formulation is absolute. Time steady and transient. Transient is when you want to do a time dependent problem. But this is we just want to do a steady state problem, time independent. Like whatever flow is going through in here, 5 minutes later it's gonna be the same flow. This is what steady means. 2D space. So this is a planar simulation. Okay, because we have a cross-sectional plane in here, and we have the whole body of the problem, the model in here. Like when do you want to use axisymmetric and axisymmetric? So axisymmetric is when you have a problem like this. Okay, so it's not good to have this kind of cross-sectional area for a circular kind of pipe. Okay, because I told you at the beginning there will be uh, errors due to no slip condition near this cross-sectional area because of this curved path. Okay, so how do you if you want to analyze for a circular cylinder, it would be a good option if you have an external flow. You can do those things like take a cross-section area like this, and it would be like you will not lose any properties or influence. But in here, if you take cross-section like this, there will be a problem. So how do you do this kind of problem? Like if you have a circular shape of pipe, what you can do is you can just take half of the cross-sectional area like this and say like the middle section is my axis of symmetry. Okay, and then it's like if you swirl the whole thing, it will be like a completely 3D pipe. So they have solved the equation and set up influence so that you can solve this kind of problem using an axisymmetric uh, swirl or axisymmetric 2D space. Okay, so if you have this kind of problem, then you wanted to do an axisymmetric space. But now we just want to do a planar because our problem is for the planar. Okay, so again, understand your problem really well. Gravity, you can apply it in x or y coordinate. You need to know. Just apply negative 9.8 or something like that. But here, the flow will not have any influence due to gravity. So because if we enable it, we are going to solve one more equation. Okay, and that's gonna stack up our computational time. If we don't need it, we're not going to use it. Okay, so we're not going to use gravity in here. Models, we have multi-phase problem. When you have solid, liquid, gaseous phase all together, you use this kind of models. We have just a single phase fluid, so we don't care about it. Energy is when you are considering temperature in your simulation, okay, like a heat transfer type of problem. Viscous, so this is important. This is the only thing you need to know for this simulation. Like what kind of model do I need to use? What kind of viscous model do I need to use? So as you can see in here, using these fluid properties and the dimensions, what I did was I calculated the Reynolds number. Okay, this is a non-dimensional number. Depending on the Reynolds number, we can say this if this flow is laminar or if this flow is turbulent. So according to the literature, Reynolds number 100 is a laminar flow. So what we want to select is a laminar model. Below the laminar models, all of these are turbulent models. Like we don't have an exact equation for the turbulent model. The Navier-Stokes, we don't have an exact solution. So that's why these are all approximate models. Like they made some analysis from some of the experimental setups and stuff like that. So they made different turbulent models which works well for different type of problem. Like the Spalatal-Maras, this works really well for external flow. Like the problem you're going to do in your project, flow around an object, this model works really well for that kind of situation. Anyways, this is a laminar type of problem. So I'm going to select a laminar model. The radiation, if you have radiation heat exchanger, these are all more advanced type of models if you need. Then I'm going to go to the material. So you can create or edit a material. Okay. And let's name it void. And you can select the Fluent database and go very bottom. As you can see, there is water, liquid, water, vapor. You can do it this way, or you can just modify this one. Like I know my density is 1, my dynamic viscosity is 2 into 10 to the minus 3. Check the units. 1, 2, E minus 3. Okay. Change your create. So it's asking me if I want to avoid. So what I did was I I really didn't want to do it, but anyways, I overwritten the air. Let me show you a different approach, because let's say this is air. Okay, let's change it back, because I wanted to show one thing. You might see that error a lot. Okay, so air is there, and now let's go to the Fluent database. Let's just drag this water liquid. I'm just copying it, and as you can see, a new fluid came in. I know my density is 1, the viscosity is minus 3. Although the properties are the same, but let's name this one fluid. Okay. Okay, this one I need to remove. Yes. Okay. So I have these two fluids in here. So what will happen when you, instead of like overwriting the single fluid, you have two fluids? Like how do you make sure which fluid is being used in this simulation? Okay. So what you can do is go to the Selwyn condition, this fluid domain. This is the surface. You remember, if you remember, we named it the fluid domain. So double click over here, and as you can see, the material used in this fluid domain is still air. But we created a new fluid, but still not in use. So even if you did the simulation was going to use the old fluid. So you need to specify which fluid do you want to analyze. Click OK. Now, let me do it this way. So let's just change it back to air. And if you go to the model, not the model. the materials. And look, if I wanted to delete the air, it's giving me an error, like it's still in use by the fluid domain. So this is another way you can figure out like something is wrong. So you can go over there, change it to fluid, click OK. And operating condition is the, as you can see, we have the operating condition is the atmospheric pressure, which is basically the same thing in here. So we don't, by default it's okay, so we didn't need to specify it. In the materials, air we are not using, so just delete it, and as you can see, it let me delete it this time. After that, boundary conditions. How do you specify the boundary conditions? As you can see, if you remember, we created inlet and outlet in the mesh. So inlet boundary condition, we're going to specify. So this is a velocity type of inlet. There are different types. I told you this is like name sensitive. So whenever we specified inlet, it by default took it as velocity inlet, not the outflow or any other type of boundary. Okay. So I know the velocity magnitude in your problem is 1 meter per second. So 1, it's an absolute velocity normal to boundary, but you can add components, x component, y component, z component. So just play around it to figure out more. Outlet, so this is a pressure outlet. So at the outlet, the pressure is the atmospheric pressure. The gauge pressure is 0, means there is no additional pressure to it. It's at operating condition, which is 1 atmospheric pressure. So at the outlet is also atmospheric pressure. So we don't need to change anything in here. It looks good. After that, other than that, we can speak dynamic mesh is for dynamic kind of like the mesh is changing with the simulation methods. Like what kind of scheme do you want to use, and like how much accuracy do you want when you're solving the Navier-Stokes equation for pressure? Do you want a third order, first order, second order? Okay, a first order upwind, a second order upwind. It's related to accuracy when you're solving the equation. Okay, we're not going to change anything in here. Reports, if you want to display some 2D plot like the velocity along this horizontal lines or anything like that, you can use these features. Anyways, by the way, monitor, residual. So how much accuracy do you want when you're solving? Basically, you're going to solve continuity, the x momentum velocity, and y momentum velocity in this problem. We are not doing any temperature or three-dimensional one, so we have less equations. So we are going to solve 3 equations in this problem. And how much decimal accuracy do we have? Right now it's 10 to the power minus 3, but you can always increase it. Okay, in here. So when they're solving this equation, it's going to be more accurate. Okay, go to the initialization. So after that, you can do hybrid, you can do a standard initialization, both fine, both works most of the cases. I did a hybrid initialization. Initialization is done. Standard initialization doesn't tell you anything. Like, yeah, it will not display anything, so don't worry about it. It's initialized. And then calculation activities, we use that for to create 3D videos, like videos of the simulation. Mostly in the unsteady cases, we use calculation activities. And then run calculation. You can check your case, or you can directly specify the number of iterations. Let's say I want to do 1000 iteration. If you remembered, like I specified some residual over there. If the residual is met before the 1000 iteration, the simulation will automatically stop. Like at 5000 iteration, 10 to the power minus 5 accuracy was met, then the simulation will automatically stop. So this is a stopping criteria which you specified in the residual. Okay, reporting interval is like how, like it's going to display it in here, the simulation progress. How does it report the reporting interval and profile update interval is that. So after specifying that, just to calculate. So as you can see, we are solving continuity x and y velocity. it's going down means, you see the residual is going down, 10 to the power minus 5 going down, and it it's converged at 140 simulation, so it didn't go through the 900 like 860 more iteration. It's automatically stopped. Okay, so our simulation is converged, as you can see. All so this is the continuity column, x velocity, y velocity. All of them are converged really well. Now to display the results, go to the contour plot. Fluent, you can display the results, but this is not a good tool for visualization. There is the results visualization tool, this one. Okay, so it's better to go over there, but some of the data you can actually check in here. Like if you want to see the velocity contour plot in the interior domain, you see, this is why I told you, like, this is not a good option because it's showing you the grids. Not, it doesn't show it like that always, but right now it's showing. And as you can see, the velocity is really low near the wall. It is high at the middle, and the flow had a parabolic shape over here, and it became fully developed after some time, and nothing changed across this the rest of the length. Okay. If you want to take like calculate any specific property, average property, you can go to the, you could have done it in here as well. Like I wanted to check the outlet velocity, let's say. So outlet velocity, I can do compute. It should show, oh, sorry, compute, no, compute. As you can see, the max velocity is this one, minimum velocity is this one. But how about I want to do an average velocity? So what you can do is go to the reports, surface integral, and area weighted average or something else, pressure. I want to check the velocity, average velocity at the outlet, compute. So this is my average velocity at the outlet. How about the inlet? Inlet is 1, which we defined as a boundary condition. So there is very small, because this is a very simple type of problem, there is not much velocity drop or pressure drop across the length of the pipe. So, but the simulation agrees, I think, with physics. So it seems okay. But if you want to verify this one, try a more finer mesh and run the simulation again and check, compare these two results. See if they are almost exactly same up to some certain decimal points. That will lead you to say like, well, my simulation is accurate. Okay, that is one kind of one way of validation. Uh, so after this one, you can save it, close it. But if you want to save, so if you close this one, by the way, if you close this one, you see it's writing the data, it's automatically saving. So if you just save it in the Workbench, it's automatically saved it in the Fluent as well. The results and everything is saved. So you can just save it in the Workbench directly. Okay. And then go to the results. Make sure to close the Fluent before opening up the results, because some of the licenses are limited, and it will it might crash due to trying to open Fluent and the results, which is called a CFD post at the same time. So it's a good practice to close the Fluent first and then open the result, just in case you might see that kind of problem. So close the Fluent first and open the results. That way it will not crash. Okay, but it might crash if you try to do it that way. Anyways, so what we want to see is a velocity profile. So as you can see, this is a contour plot of, let's say, velocity. Where do I want to see this contour plot? In the domains, location is symmetry. So this is my surface. But if you don't see the surface, I'll show you how to create a plane. Variable, I want to check the velocity. Contours, this just refines stuff. Okay, so you can play around it. Range is, you can limit the range. Click apply. See, this is a lot better tool to visualize for visualization. So this is the velocity, and this is the values. Let's. I'm just changing the same thing for pressure. So this is how the pressure is changing, which looks reasonable as well. Okay, and let's say I didn't have the symmetry one. How do we create a plane? So you can go to the location, select a plane, and it's an XY plane with z coordinate 0. So it's going to be the same thing. It's going to slide, click apply. As you can see, the plane is there. So if I double click on this one, instead of symmetry, if I do a plane, you see it didn't change because the plane is the same thing. So this way you can create a new location, like maybe a line over here, and check like how it's the average velocity or anything like that over there. So you can do all kind of, you can just play around using these tools to display your result in a better way. That would be all for the initial simulation. So hope you can get started and let me know if you have any questions regarding it. All right. Close this one.